So here we go. So this first one's a cantilever beam. So what we want to do is we want to come up with equations for these. We got any questions on this one specifically? So the first thing you want to do is come up with reactions. Okay, that's a cantilever. So you want to some forces in the x, some forces in the y, and some moments. What you're doing, a cantilever has what I call a reactive moment at the wall. So the load on that beam is trying to make the beam swing clockwise, so the reaction has to be counterclockwise to prevent it from doing that. It has to be developed by however it's supported at the wall. So we just get sum of fx is 0 is rax, sum of fy is 0 is ray minus the 2400, minus the 8,000, which is the load there at B, and then minus the area of the loading diagram, which is 24,000. So the RAY is 32,000 up, and then you go sum of MA equals 0. You get the reactive moment there at the wall, which is right there. That's coming around, preventing that clockwise motion of the beam. And then you got the 24,000 times its centroidal distance, which is half of 6, it's 3. And then the 8,000 times its moment arm, which is 4. So you come up with the reactive moment, it's 104,000. So that's where you'd start with the reactions. And then once you've got them, what you want to do next here is to draw up a free body diagram of each of the pieces. Now you're going to have to do two pieces, one from A to B that does not include the 8 kilonewton load, and then another piece from B to C, which does include the 8 kilonewtons. See, the 8 kilonewtons is why you need two separate sets of equations, because it changes the free body diagram. Okay. So the first one there, I'm going to start at the left. I always set x equals 0 at the support, so that's point A. And then I'm working my way out towards B. So I show the reactions there on the left, the moment reaction and the force reaction. And then I've got the load, which is 4,000, but it's down, so I'm calling it negative 4,000, for that reason, because it points down. And then you start with x equals 0 at the wall. At the far left of the beam is the convention. Then you just work your way out a distance x as you go. So this, and then you've got the internal moment, which curls the beam up, so that's counterclockwise. And the internal shear points down by convention. So that free body diagram there would hold anywhere between A and B, just short of B. All right, and then you just, once you've got the diagram, you just sum forces in the Y. 32,000 is the reaction, so that's up, minus the 4,000 times the distance over which it acts, which is x, that's down, minus VAB. So you can solve for VAB, it's negative 4,000x plus 32,000. Okay. Now these are the areas here, at least in one area of the 4,000x. So when I do the moment equation, I take the moments about the cut, okay? That's kind of important. I'm taking moments about here. And I just look at that diagram and start adding up the moments. So I've got 104,000. For the reaction, I've got 32,000 times x. That's going to come around clockwise, so that gets a positive. I'm sorry, negative. It's clockwise, so that's negative. And then I've got the 4,000x that I found right there, and then that'll have a moment arm of half of the base of the rectangle, which is x. So that's going to be applied right there. So that moment arm will be x minus 2, and that would be positive. Okay? So then I just bring the MAB to the other side of the equation, collect terms of what's left, and multiply through by negative 1, and kind of order the terms in the proper order, and I get that moment equation. Okay? That's the process. So we doing all right with that? Any questions on that? So that's the basic drill for doing this stuff. This is, these types of problems typically get very detailed. So we want to, kind of slow down, get very systematic, draw pictures, all those things that we like to do so we don't make the careless error, or whatever the errors are, and those are just good habits like we want to develop for this stuff. So I'm conscientious about how I work through things when I do these with the intent of avoiding errors. Okay. So we good with that? Okay. Now the next one's similar, except now you've gone beyond the 8,000. So you draw another free body diagram from B to C, and you pick up the 8,000 Newton load. Now when you do that, then X again is always 0 on the left. That's kind of a convention on this. And then as you work your way to the right, you've got that distance X. Now I do have an actual distance here to the 8,000. It's 4. It's not a variable. It's a number. It's 4. So what that means is this little piece in here is X minus 4. The total's X, and you've come 4 back. So that piece from the cut to that load is X minus 4. Okay. And then you just follow a similar process that we did up above. You got the reaction up, 4,000 times whatever X is down for the distributed load. We pick up the 8,000 and then minus VBC. The shear equations always work out pretty nicely because you got minus VB, minus the shear, because you're putting that in its positive shear sense, which is down, which is a little odd, but that's how that is. But then here, this is a statics equation. So when you put it in the statics equation, it's minus. That's kind of what's going on there, okay? And see, that's not all bad, because when you bring it to the side of the equation, the negative becomes positive, and you got whatever's left on the right side is your shear equation, okay? So, we doing all right with that? So we got any questions on that? And then the moment equation there, often I look at the shear equation because it has areas on it which represent the loads. So when I do the moment equation, I got the 104,000 positive. I've got minus the Y reaction times X clockwise. Then I've got plus that downward load, which is the 4,000 times X. Okay, it's shown right there. Then I need a moment arm for it, and that's in a rectangle. That's in the middle of the rectangle, which is a moment arm of X over 2. That's what that is. And then I've got the 8,000 times X minus 4. That's a positive, because that's coming around counterclockwise too. And then plus MBC. And then I just work through the algebra there and solve for MBC. And as I've mentioned, a good check is always the derivative of the moment should get you to the shear. Okay. So we got any questions on that one? All right, so that's the first one. All right, the one after is a little tricky too. What you're going to want to do on that is get the reactions. They're going to be 5,400 and 10,800. You're only going to need one cut for this because it's just a triangular load down. So, but the cut you make gets a little bit involved. So we got 10,800 at A for the reaction, and then 5,400 at B. Okay. All right, now here's how this goes. When you're going to make a cut anywhere between A and B, it's all the same free body diagram, so there's nothing, Nothing to, you don't have to look at how you're going to break the diagram up, it's just one. But you're going to have to figure out what the height of that point is wherever you make your cut. Because, you've got a triangular load from A to B, but what that creates is when you make a cut somewhere is a trapezoidal load. And to handle that, you're going to want to run a horizontal across and turn that into a rectangle and a triangle is what you're going to want to do. Okay? So you got to know the height of that point. Now the height relates very much to the slope. Okay, so what that line does is it drops 3,600 over a run of 9. So the slope of that line is negative 400. Okay, so wherever you cut that diagram to start building this diagram, you're going to drop by the slope times the distance, which is x. All right. So the height of this point here is going to be the 3,600 where you started on the left-hand side minus 400 times whatever your x distance is measured from the left. So that's going to give you these two shapes. The rectangle on the bottom has a base of x and a height of 3,600 minus 400x. And the triangle on the top is just going to have a height equal to the amount of drop. It'll be 400x. And then you're going to have the centroidal locations. For the triangle, it's a third of the base over from the right angle. For the rectangle, it's half of the base. Okay? So then what I went ahead and did there was I found the area of both shapes based on that information. The area of the triangle is 1/2 times 400x times x. It's 200x squared. That's the area of the triangle. And then the area of the rectangle is the 3,600 minus 400x times the base of x. So it's 3,600x minus 400x squared. So I got everything lined out there now. As those distributed loads, I've broken that down. The trapezoid, I've broken it into two loads at the centroidal locations. I'm going to have the reaction over here, the 10,800, and then I'm going to have the shear and the moment. Okay? So a lot of the work on this one is just getting to that point right there. Right? Once you've got there, it's just a matter of writing up the equations. So we got any questions on that, setting that thing up? The whole deal on that is about the slope of that the line on the hypotenuse of the triangle. It's dropping 3,600 over a run of 9. So the slope is negative 400. And then you multiply that by the distance, which is x, that gets you the change in height. So we're at 3,600 minus 400x. That's the height of that point there on the right. And then based on that, you can come up with the height of the rectangle, which is 3,600 minus 400x, and the height of the triangle, which is just 400x. Okay. So we're good with that? So then it's just sum of Fy is 0, 1,000, 10,800 up, right there, minus the 200x squared, minus the area of the rectangle, which is 3,600x, minus 400x squared, and then minus the VAB, and solve for VAB. And then the moment of the cut, remember, or excuse me, moment about the cut, because that's where you take the moments about, is wherever you've cut the figure over here, right there. Take moments about that point. You get 10,800 times x, that's negative. And then the 200x squared will be not times x over 3, but it'll be times 2x over 3, because here's the moment arm right there. So that's 2x over 3. That's the moment arm for the triangular load there. And then you've also got a moment arm for the other one here, which is the rectangular load. So that's going to be the 3,600x minus 400x squared times its moment arm of x over 2, which is the distance right there. Okay. And then you got plus MAB. Run through and solve it out, you get MAB when you collect terms and do all that stuff. Okay. So, I guess the thing on this that I'm seeing is part of it's figuring out these equations and all that. The other part is we're doing that thing that engineers do. We got this kind of complicated, long problem. We're just focusing on one little step at a time. We're not getting too far out of the box what we're thinking about. Just step, step, step. Get a picture, label the picture, and then build the equation. Slow, nice and slow and easy, so to speak. Okay. And that's the equations there that we use sometimes. So we good with all that? Okay, good. Now the diagrams are a little, they represent the same thing, but they're done differently, okay? Diagrams are based on rules. So the next one here, I think it's 341, is that correct? I think, yeah, 341. We want to come up with the reactions. So what we have over here, if you remember from statics, is called a couple sometimes, a pure moment sometimes, whatever you want to call it. It's just a twist of 24,000 Newton meters counterclockwise. Oh no, that's clockwise, isn't it? Okay, then we've got the load, and we've got a simply supported beam, so we go sum of F, sum of MA to get the reaction at D, and then you can just go sum of Fy after that to get the reaction at A. So 4,000 and 5,000. The one thing on these equations is you want to be darn sure you get the proper reactions. So, take your time on those and be sure that they're right. Because if you have bad reactions and you start trying to do diagrams, they often go kind of south on you. So you want to just be sure you get good reactions. So 4,000 and 5,000. All right, so now you can go ahead and build the shear diagram after you got the reactions. So what you're going to do then is you're going to come up from 0 to 4,000. Nothing happens there. There's nothing on there to change the shear until you hit the 9,000. That will drop you by 9,000. So you get from 4,000 down to negative 5,000. Okay. Now that couple does not directly affect the shear diagram, so the shear diagram just goes straight across because that couple doesn't affect it, and there's nothing else on there that will. And then that gets you to negative 5,000 on the right, and then this reaction pulls you back up to 0. Okay. Now so we good with the shear diagram there? You have to ignore the couple on the shear diagram. Now the couple does affect the reactions, which indirectly affects the shear diagram. But other than that, the couple has no effect on the shear diagram. You just go right over it as though it's not there, okay? All right. Now I know the couple will affect the moment diagram, so I'm gonna, instead of getting one area there, I'm gonna get two, because whenever I see blocks and areas like that, I wanna find what the areas are. Okay, the first one there on the left is 4,000 times 4, it's 16,000. The next one is negative 5,000 times 4, that's negative 20,000, as is the one after that. So I'm breaking that into two pieces because I see that couple right there. I know that's gonna jump the moment diagram. So I want to find the area either side of that couple. That's what I'm doing. All right, so I go from 0 up to this amount of area, which is 16,000. I do that at a constant slope of 4,000. So the value of the shear diagram is equal to the slope of the moment diagram. So that slope is just constant, so it's a straight line. Then what happens next is I hit this first block. It's got an area of negative 20,000, so that takes me from 6,000 down by 20,000 to negative 4,000. Then I hit this couple, and that's 24,000. Now that's actually negative 24,000, but what that's going to do to the beam right after that couple, after the beam sees that couple, the beam's going to react the other direction. The beam's going to do that and have a positive reaction to it. So that makes the moment diagram jump up by 24,000 immediately. Okay, so that's because the beam is reacting to that couple that's applied. So you do have to remember that one thing, that a couple causes an immediate jump in the moment diagram, and two, that it's in the opposite direction of the sign on the couple. So that's a negative couple because it's clockwise, so the moment diagram jumps positive, okay? And then the last little bit there, you go back down by this area, 20,000, back down to 0. Okay. So what that couple does is it causes a discontinuity in the graph. See that? That's just a straight line with a constant slope. The slope there on either side of there is just equal to the value of the shear. It's negative 5,000, and the slope here is the same thing. But you get a break in the line because of that couple. It just kicks the line up 24,000 is what it does. You doing all right with that? Okay. Okay, the next one here, you want to get the reactions. You know, we did that on the previous homework problem. I get the total area, negative 4,000, because that's actually pointing down, times 6. 2 and 4 and 2 make 6. It's negative 24,000. Okay, that's the area. Also, I know this load here is going to cause a jump in the shear diagram, so I get the area on either side. So I got the negative 4,000 times 4, it's negative 16,000. Negative 4,000 times 2 is negative 8,000. So I get both of those areas in there. Okay. All right, so that's the stuff I'm working with. I've also got the 32,000 and the 104,000 on this. So I got the couple of 104,000 and the load of 32,000. All right, so what's going to happen here on the shear is I'm going to start at 0. I'm going to go up 32,000. Then I'm going to drop by 16,000. So that'll get me down to 16,000. Okay, so I'm at 32,000. I drop by 16,000. Now the slope here is equal to the value of the shear and the value of the load, I should say. And that's negative 4,000. So that's a constant slope, so it's a straight line. Then I've got 8,000 down, so that gets me from 16,000 down to 8,000. Then I drop by 8,000 more at the same slope of negative 4,000, so that gets me down to 0. Okay, so there's the shear diagram. Doing all right with that? Okay. All right, now again, I've got an area of shear. So what I'm going to want to do is block that off, find the area to the left and the one to the right. So I've got a trapezoid, so I can take the height on the left plus the height on the right, get the average. So I add them together, divide by 2. That gets me the average height. And then multiply it by the base, which is 4, and that gets me that area is 96,000 there. All right, and then the area of the triangle on the right is 1/2 times 8,000 times the base at 2, it's 8,000. Those are positive areas. Now if you look at what's going to happen with that beam, these loads are going to bend it down like that. So that's a frowning beam, so to speak, so that's negative moment, okay? So that's why the whole diagram here is negative. So what's happening here is you're hitting that counterclockwise 104,000. That's the first thing that you encounter on the moment diagram. So that takes the value of 0 and it takes it down to negative 104,000. Then you're going to change by a positive 96,000, so that'll get you up to there, okay? So that's negative 104,000 plus 96,000 is negative 8,000. Now the slope here is changing The slope here is what, 32,000, which is quite positive. The slope up here is less. It's 16,000. So the slope becomes less positive. So that makes that line kind of flatten out and get more horizontal. It's not horizontal yet, but it's becoming more horizontal than the way it started. So that's concave down. Okay. Then you get an immediate discontinuity. I don't think the beam really cares that it's, there's a discontinuity there, but it is there. So you get slope at 18,000 and then slope at 0. So, what I mean by that, it doesn't have any real effect on how you design the beam. It's not like it causes a stress concentration or anything like that. It's just, but it's there all the same. Your slope goes from 8,000 to 0, which is flat. So it's kind of approaching an asymptote if you want to think about that in mathematical terms. The x-axis there out at the end of the beam. And the moment changes by an amount equal to the area under the shear diagram, 8,000. So you go from negative 8,000 to 0. That's where you go. All right. So that's that one. We got any questions on that? Okay, the last one's a bit tricky, so we'll look at the last one too. Triangular load, we already have the reactions. 10,800 on the left and 5,400 on the right. Now we went over one of these in class and I gave you that note sheet for it. I don't know if everybody has one of these. I don't know if everybody does or not. I think it's a similar process. You're going to have to look at that. So that's going to be required because we're starting off. All right, so it's a similar kind of thing here. You've got this triangular load. That's a linear function. So the next step will be a parabolic function because what you're doing here are graphical integrations. So each step of the way, the power on the function of the line increases by 1. So that's kind of a y equals mx kind of thing, plus b. All right, so that's x to the 1. Your shear will be x to the 2, a parabola, and then the moment will be x to the 3, a cubic. Anybody else need one of those? I mean, that was just for the example in class. We're good. All right, so what I want to do here is figure some things out about that triangle. Now, the thing that I'm going to figure out here is that I want the area of it. Now, be aware that the diagrams for loads are often shown over the beam, but what you really care about as far as the sign goes is the direction of the arrowheads. Those arrowheads point down, so that's a negative area. 1/2 times the 3,600 on the left times the span of 9. So it's negative 16,200, okay? And that's located at 3 meters over, of course, because the centroid's 1/3 of the 9 from the right angle. Okay. So now I want to, that'll get me kind of what's going on there with the shear diagram. I know that I'm starting at the reaction, which is 10,800, and I know I'm going to end up 16,200 less than that, so that's negative 5,400. Okay. And then I know that my slope starts off negative and ends up at 0, so that I can tell that that's going to be concave up, because I got a negative slope and then it flattens out to 0 by the time I get to the right. Now the issue is the next step. See, I got to get to the moment diagram. Now to do that, first thing I got to know is where this zeroes out, because I got negative area to the left, positive area to the right. The other thing is I want a function for that line, because I'm going to have to integrate that thing to find the area. So those are a couple of things that I'm thinking about here. Okay, so, and the key thing to understand about this stuff is that I want to find the area of this shape as I work my way to the right. Okay, that's really what I want to do. So I tend not to call the base of it x. In this case, you can because x is 0 on the left, but in that example in class, it wasn't, okay? And if you start using x for some of these functions, it can get pretty messy pretty quick because you kind of have to use something like x minus 3 or something like that to plug in, and that just kind of makes the equations more complicated. So generally what I do on these, I just use b for base. In this case, b and x are the same thing, but generally speaking, I just call it b, and then I'll fix the offset for the x later. That's usually how I look at these. This is not an issue on this problem, but it wasn't the one we did in class, okay? So I just want to point that out. It just simplifies my equation. I don't want to get it too messy, okay? So what I want to know then, see the area under the load is the change in the shear. So what I want to do then is figure out, as I work my way over from the left to the right, what's the area under that loading diagram. So I've got the height on the left, it's 10,800, but I need the height on the right, okay? And the way I'm going to get that is I'm going to need the slope of that line. All right, now the slope of the line is, and we already looked at this when we did the equations, the slope is what I want. And what the slope does is it drops, so I'll put a negative in there, 3,600, because I'm going from 3,600 to 0. And it does it over a run of 9, so the slope is negative 400. Okay. So what that means is this value right here is 10,800 minus 400 times whatever b is. So that's the height of that diagram as I work my way across. You okay with that? Okay. All right, then I'm going to want the area. That's the next thing I'm going to want. So we're good on that? And hang on here. No, I busted that. I don't want that reaction up there. I'm sorry, screwed up. I want 3,600 up here, and that's what that is. And this is going to be 3,600. My bad on that. There we go. I had the wrong number in there. The height is 3,600 on the left. That's what I want, okay? All right. So now the area under that thing, and let's just go ahead and do that. That's going to be 3,600 plus 3,600 minus 400b over 2. That's the average height. So what I've got there, I've got 3,600 on the left, and then I've got 3,600 minus 400b. That's the height on the left. So if I divide those by 2, I get the average height of that trapezoid, which is what I'm dealing with here. And then I would multiply that by the base, which is b, and that is the area under that loading diagram. So what I got there, I got 3,600 plus 3,600 over 2, that's just 3,600, minus 400 over 2, 200 times b, and then I'll multiply that by b, okay? So what I'm going to get then is I'm going to get 3,600b minus 200b squared. Okay. So that's the area there. Okay. So if I want the equation there, so now I've got the area. That's the change in the shear as I work my way across, because the change in shear is the area under the loading diagram. So now what I can do is I can take the value of shear on the extreme left, where that triangle starts, which is 10,800, and subtract off that area, because that area is actually pointing down and the shear is decreasing as I work my way across. So I'll take the 10,800 on the left minus that area. Okay. And then what I'll do, if I want to figure out where this zero is, well, I'm going to make that into an equation for starters. So here's the equation. I've got the terms in the order that you normally have a quadratic ordered in. So I got the 10,800 on the left, and then I'm going to have minus a negative 200b squared, so that's positive 200b squared, then minus 3600b. So that's the equation of that line. So what I want to do first is figure out where it zeroes out, because that's that boundary between positive area on the left and negative on the right. So what I'm going to do is take that equation and set it equal to 0. And then I just do the quadratic on it, and I get two values, 3.8 and 14.2. Now I get two answers because it's a quadratic, but the other reason is that it's a parabola, right? So if I just track that parabola out, it'll end up out here. So the other values intersecting out there at 14.2, okay? Of course, you know, these equations I'm running don't have any native intelligence to them. They're just equations. So it doesn't know that's out of the bounds of my beam. That doesn't count, okay? I don't want that one. I want the 3.8. That's the one I want, okay? Because that's the one that's in the bounds of my beam from 0 to 9, okay? So that thing zeroes out at 3.8. That's the bottom line on this. And see, I want that because it's a limit of integration, because I'm going to find the area of that thing by integrating it. So what I'll do then is I'll run an integral for that. So I'm going to go from 0 to 3.8. And I'll run that equation of the line. 200b squared plus 3600b plus 10,800. And then I'll have a dB in there. And I'll just integrate it. So I'll get 66.67b cubed minus 1800b squared plus 10,800b, and I'll evaluate that from 0 to 3.8. And that comes out to be 18,037. Okay. All right, then I can run it from, and that gets me 18, that's the positive area there on the left. The negative area on the right will be the same equation evaluated from 3.8 to 9, from here to the limit there. And that will come out to be a negative 18,737. So what's going on with the moment diagram then is I'm starting right there on the left at 0. I'm going up by an amount equal to the area of this first shape here, right there. That's positive area, so that makes my moment diagram go up. I've got a very extreme slope here. I don't ever try and draw these to scale because the slopes are often just so extreme. It's 10,800, and then I've got a slope of 0 at the top where it maximizes. And then what's going to happen next is I've got this shape here, and the area of that is negative 18,737. If you're actually running these numbers, it's very possible you might have a little bit of rounding error in there, but you know, we don't get too worried about that, okay? So that last bit, then take the change in, or the area under the shear diagram is the change in moment, and that takes it back down to 0. Okay? And then looking at the slopes, you can see that that'll be concave down. Okay? So do we got any questions on that one? So that's the shear moment equations and diagrams. Is, you know, we're seeing from what we're doing now, we use these. We use them to find the bending stress, and we use them to find the shear stress. That's why we want to know these, because we want to know what those internal forces are, because they're the things that lead to the stresses, okay? So when you look at these shear moment diagrams, you can very easily, once you've got them derived anyway, pick the high value. You design that beam for a moment of 18,737, and that would be for the moment, and for the shear, oh, no, it'd be up here, 10,800 is what you design it for, okay? And you can tell how the shear and moment vary as you go across the beam. All right. So that's a little bit there on shared moment equations and diagrams, okay? Just a tool that we use to figure out what's happening there with beams. So, any questions on that? All right.